Okay, thank you very much. So in this lecture, I will try to give an introduction about several features of gravitational theories involving massless higher spin fields. And in particular, their role in the AdS CFT correspondence. So here by higher spin, I will of course mean spin greater than 2, 2 being the graviton. And the problem of writing down consistent equations of motion and Lagrangians for fields of arbitrary spin is of course a very old problem. It dates back to the beginning of quantum field theory. It was understood very early on that at least theoretically fields of any spin exist because there are a unitary representation of Poincare group of arbitrary spin. So it was one of the early problems of quantum field theory to try to write down consistent equations of motion for these fields of arbitrary spin. And people like Dirac, Pauli, Firth, Bargmann, and Wigner worked on this problem. So the problem of writing down consistent equations or Lagranges, and in particular consistent interactions, is particularly difficult for massless fields. This is because massless fields, so massless fields of spin greater or equal than 1 are gauge fields. So if we represent a spin S gauge field by a symmetric tensor with S indices in the language of field theory, if the field is massless, there is an associated gauge invariance which is needed to decouple unphysical polarizations. And this gauge invariance is the generalization of the one you're all familiar with for spin 1 and spin 2. So for an arbitrary spin S field, say in flat space, there is a gauge invariance with a gauge parameter of spin S minus 1, which is this epsilon. It has S minus 1 indices. It's symmetric and traceless. And so this is just a generalization of the gauge invariance for spin 1 or spin 2, the gauge invariance of linearized gravity. Okay. So due to the presence of these gauge symmetries, the problem of writing down consistent interactions for these fields become very highly constrained and very complicated. So let's see how they use this. In flat space, can you all see, by the way, if I write this size? Yeah. Oh, okay. Okay, so in flat space, of course, as you can expect, we can write down a consistent gauge invariant equation of motion for free fields. This is Fransdal equation, which we will review later on. But if we want to look at interactions, one can see that it's very hard to write down interactions of massless higher spin in flat space. And in fact, it appears to be impossible to have a non-trivial S matrix for spin greater than 2. And this is essentially because for these higher spin fields, due to this gauge invariance, there are associated conserved charges of spin S minus 1, which should annihilate the S matrix. So there are conserved charges of spin s minus 1. And these conservation laws for spin greater than 2 are too strong and only allow for a trivial S matrix in flat space. For spin n1 and 2, of course, we know that we can have non-trivial interactions. We have Yang-Mills theory, and we have Einstein gravity. But for spin greater than 2 in flat space, the existence of these conserved charges only apparently allows for a trivial S matrix. And this is essentially consequence of the Coleman-Mandula theorem. Okay. Can I also use the side blackboard? Okay, so this is in flat space. On the other hand, so people, due to these results, believe that we don't have to worry about higher spin particles because they cannot have non-trivial interactions, so we can only describe trivial theories with it. But on the other hand, there were some explicit constructions if we go away from flat space and we allow for a non-zero cosmological constant. So if we work in anti-de Sitter space or de Sitter space, there are, if you want, yes, go explicit results due to Fradkin and Vasiliev, and mostly to later work of Vasiliev between 89 and 92, who was explicitly able to write down a theory of consistent interacting higher spin fields assuming non-zero cosmological constant. So consistent, fully nonlinear equation of motion for higher spin, massless higher spin fields. Okay, so we will review the construction of this theory probably in the next lecture. But what is remarkable is that by an explicit construction, Vasiliev was able to derive this consistent set of equations of motion, and they describe interactions of fields of all spins in anti-de Sitter or de Sitter space. Okay, so we know the full equations of motion. One important thing about these theories is that in particular they are theories of gravity. Okay, they always contain spin 2. You cannot avoid the spin 2. So they are in particular theories of gravity. There is always a spin 2 particle in the spectrum. Okay? Another important feature of these theories is that they involve infinite towers of fields of all spins. Okay, so as soon as you try to introduce a field of spin greater than 2 and try to write down consistent nonlinear equations of motion, you discover that you need an infinite tower of them. You need 3, 4, 5, and so on. In the bosonic cases, there is also cases in which you have higher spin fermions and so on, but the general feature is that you never have a finite number of fields. You always have an infinite tower of fields. Okay? Let's see. I need to get used to this. Okay. So I said that these theories are in AdS. More precisely, what Vasiliev wrote down are a set of equations of motion which are background independent. And AdS or DS is particular vacuum solutions of those equations of motion, as we will see next time. So to study what is the spectrum of these theories, one first realizes that there is an AdS solution, and then studies linearized perturbation above that solution, and that will show what is the spectrum of these theories. And for example, in the case of AdS4, Vasiliev theory, bosonic, which is the theory I will mainly concentrate on in these lectures, although I will mention generalizations. So in this theory, for instance, the spectrum of fields propagating on the AdS vacuum consists of massless fields of spin s equal to 1, 2, 3, 4, and so on, all the way up to infinity. And moreover, there is an extra scalar field, which is also a prediction of the construction. This scalar field cannot be projected out. It's there in the spectrum, and it has a mass which is fixed by the equations of motion. And in AdS4, it has a mass equal to -2 in units of the AdS radius. Okay. Any questions so far? Okay. So this, just as a comment, you have noticed that this mass square is negative. However, in AdS, this is not a problem as long as this mass square is above the so-called BF bound. And the BF bound in AdS d plus 1 is, for a scalar, is m squared greater than minus d squared over 4, which is, in this case is minus 9 over 4, which is below this. So this is a good scalar field in AdS, has a mass square which is above the BF bound. It also turns out that this value of the mass square corresponds to a conformally coupled scalar field in AdS4. Okay. Okay. So this is so what Vasiliev wrote down are equations of motion. So this is a classical theory. However, even though this is not well understood so far, one may hope to understand how to quantize this theory consistently. And then, due to this very large symmetry that the theory has, which is this higher spin gauge symmetry for all these spins, one may hope that due to this very high degree of symmetry, this might be a very well-behaved theory of gravity, maybe a UV finite theory of quantum gravity. And even though this is still a question mark, as Igor mentioned in the talk yesterday, we do have evidence that this is true at one loop level, where to this order the quantization is simple because we can just compute partition functions using free field kinetic operators, as I will review later on. And in actually in any dimension, we have verified that these Vasiliev theories are indeed UV finite at the one loop level. Okay. Okay, so even though the existence of these theories may look surprising, given that we know of all the difficulties of building such theories in flat space, it's actually natural to understand why they have to exist if we think in terms of AdS CFT. So Vasiliev constructed this theory well before AdS CFT, definitely didn't have AdS CFT in mind as a motivation. But from the point of view of AdS CFT, it's quite natural that these theories had to exist. And if they didn't exist, there would be a problem with the general law of how we understand AdS CFT. So let me try to explain why. Okay, so yesterday Igor reviewed how the original example of AdS CFT could be derived from D branes in string theory and so on. But we believe that AdS CFT might be something more general than that. In general, it could just be understood as some relation between any theory of quantum gravity in AdS and the theory and the CFT, or in general some field theory without gravity at the boundary. And this quantum gravity theory could be a string theory. In examples that we understand well, this is a string theory. But this might be something more general. It may just be a correspondence between quantum gravity in AdS and the CFT at the boundary of AdS. So if Vasiljev theory describes some gravitational theory in AdS, it's natural to ask what would be the conformal field theory dual to it. And well, the answer is quite simple. This which is quicker. So let's consider the case of D equal 3, since I was discussing the Vasiljev theory in AdS4. And so let me take a theory of n massless scalar fields in D equal 3. So I take, I collect them into a vector phi I, where I is an index going from 1 to n scalar fields. Let me take the scalar fields to be complex and massless. So we just, for now, take a free action. Okay. So just a very simple free action of n scalar fields. Of course, this is a CFT. It's a very trivial CFT, n massless scalars on R3. And so this theory has a UN global symmetry where this phi I transform in the vector or fundamental representation, which I'll denote as a box. Okay, so this kind of CFT is different from the type of CFT that Steve was discussing yesterday, which are of Yang-Mills type and where the fields are in the adjoint representation. Here, taking fields in the fundamental representation for reasons that will become clear soon. So we call this a vector model, meaning that this field is in the vector representation of UN. Okay, so any questions about this? Okay, so why this theory is related to the higher spin theories in AdS? Why I'm talking about this very simple free theory? Well, it's not difficult to realize that this theory, by virtue of being free, has a very large number of conserved currents. These conserved currents are just bilinears constructed from these phi's and several derivatives. So consider an operator of this kind, mu1, mu(s), which is totally symmetric and traceless, which is schematically this form. And this expression is only schematic for now. I can give you the precise expression in a second. So this just means that it's a bilinear with S derivatives. These derivatives can be distributed in several ways between these two fields. And the operator is traceless. And then one can show that, well, provided these derivatives are distributed in the right way, there is such an operator that it's conserved. Okay? So we call this a conserved higher spin current. And the conservation just follows from the free equations of motion for phi, as you can check once I give you the precise expression for these operators. Okay, so the conformal dimension of these operators, since this is a free theory, is the one that you can read off from the expression of this current. In 3 dimensions, scalar fields have dimension 1/2, as you can see from the action. So the dimension of this operator is s plus 1. So even though I'm doing this in 3 dimensions, you can see easily that you could say the same things in general dimensions. And in that case, the conformal dimension of these operators would be s plus d minus 2 for general d. Okay, so for instance, where is it? This is tricky. Okay, so for instance, examples of these general currents for spin 1 and 2 are very familiar example. So for spin 1, this is just the usual U1 current. The usual expression you're all familiar with, current which follows from U1, the U1 invariance of this action. And for S equal to J mu nu is just the stress tensor of this CFT, which has the following explicit expressions. Let me write this in general D, and you can specialize easily to D equal 3. Okay, so this for S equal 2 is the precise expression for those operators, where there I just wrote a schematic expression, and here I wrote the actual expression of what the operator looked like for S equal 2. This is how the derivatives are actually distributed. And you can check as an exercise that this stress tensor is conserved and traceless. Okay. One way to understand the presence of this term here, which may look unfamiliar to you, is that it comes from, so one way to compute the stress tensor for any field theory is to put the field theory, couple it to an arbitrary metric, and then take the functional differentiation with respect to the metric. Once we couple that CFT to the metric, in order to do it consistently with conformal invariance, we have to add a conformal coupling of the scalar to the curvature, to the Ricci scalar, r phi square. And once we differentiate with respect to the metric and set the metric to be flat, in the end, that will produce this term. And this coefficient here comes from the conformal coupling. Okay, so you can do that also as an exercise to derive this stress tensor from that Lagrangian, adding the r phi square term. Okay. Okay. So for completeness, let me also give you the general expression for the general spin S currents. It's given by this. I'm afraid that I will not be able to write this here. Okay, so this is just for completeness the expression for these conserved currents. One way to derive it is just to write down the most general bilinear with S derivatives and impose current conservation and tracelessness. If you do that exercise, you'll end up with this solution. So this is for general D. Again, here we are in D equal 3, but we can do everything in general D. Okay, and you can check that for S equal 1 and 2, this expression will give you this. Okay, so we have these conserved currents in this theory. Notice that these conserved currents are invariant under the UN symmetry. They are UN singlet operators. And let me go here. So these JS are UN singlets. And borrowing a terminology that we are usually used for matrix theories, we can say that these operators are single trace operators in the sense that there is only a single sum over this UN index. Okay, so these are the analog of single trace operators that we have in joint theories. We will use the same terminology for vector models. And if we ask the question of what are all the UN single trace operators, then one can show that these are the only single trace operators if in addition we include a scalar operator in which I'm using the same notation J, even though this is of course not a current, it's just a scalar operator, but just to use uniform notation. So this J0 is the scalar operator delta of dimension delta, which is 1. Okay, so this J0 plus all these higher spin currents is the full single trace spectrum of this vector model. Okay? Now, the reason that single trace spectrum is important is that in AdS CFT, in the usual way that we understand the dictionary of AdS CFT, single trace operators in a CFT are dual to single particle states in AdS. So if we want to compare the spectrum of particles in the AdS theory, we have to look at the single trace spectrum first, and each of those single trace operators should be dual to a single particle states in AdS. But now we can see that this single trace spectrum is precisely in correspondence with the spectrum of the Vasiliev theory in AdS4. Sorry. So let me summarize what I just said with a table. So here, single trace operators are dual to single particle states in AdS. So here I'm just writing down general dictionary of AdS CFT. And if we have a conserved current, of spin S, so in general conserved currents will be dual to gauge fields in AdS. So here we must have a spin S gauge field. So a massless field phi mu1, mu s with an associated gauge invariance which is related to the conservation of these currents in the boundary theory. Okay? And if we have a scalar operator, that will correspond to some bulk scalar field. And if this operator has dimension delta, the bulk scalar field will have a mass which is given by the usual relation, m squared equal delta, delta minus d, where d is the dimension of the CFT. So now you can see that if we look at this particular free vector model, its single trace spectrum precisely corresponds to the spectrum of Vassiliev theory here. There are massless gauge fields, one for each spin, and those will be dual to those currents, one for each spin. And then there is in addition a scalar field of mass square equal minus 2, and that's precisely the mass square that you get here if you set delta equal to 1, and which is the dimension of this scalar operator, and d equal to 3. That gives you m squared equal minus 2, which is the mass that we expect. Okay? So any question about this? Yeah. I'm not, I didn't discuss interactions yet, so I didn't discuss that yet, okay? So far I'm just comparing spectra. So let me discuss now about interactions and N, okay? Sorry? You can. So I will discuss this as comment in a while, but so you could consider a free matrix theory. That theory will have conserved currents because it's free, but in addition there are many more single trace operators. The important feature about vector models is that the spectrum of single trace object is very restricted. We have only these bilinears. If we have a matrix theory, you can write down single trace operator by writing a trace and any number of product of any of those fields. And those operators are not all conserved currents. Only a subset of those are conserved currents. So for that theory, the dual will be more complicated. It will not be a Vassiliev theory which only has this spectrum. There will be many more operators which are dual to those extra, many more fields which will be dual to those extra single trace operators, like trace phi to the fourth, for example. That will be dual to some massive field in the bulk, which is not present in the Vassiliev theories. Yes? Would that apply to? Well, here I wrote down the bosonic theory. There are versions in which you have fermions. The fermion that you get, so in particular, there can be a spin 1/2 massive fermion. The mass is always above the corresponding BF bound. There is a different bound for fermions. Yeah. Any other question? Okay. Okay, so this is just about the spectrum. So far, well, this shows that if we have this free CFT, it should be dual to some theory in AdS, which has the spectrum of massless higher spin fields. But to really show if these two theories are really dual, you also should look at interactions and see, for example, compare correlation functions of operators on the CFT side to like amplitudes in which these higher spin fields interact. So first of all, let me clarify one thing. So this is a free CFT, so one may expect that everything is trivial, but of course, if we look at, oh, no, cannot write this, sorry. Okay, so one confusion that's one may have is that this is a free CFT. How can it be that this is an interacting theory? Maybe this is a free theory. But we know that Vasiliev theory is not a free theory. It's a highly nonlinear theory in which the higher spin fields interact. But that is just as expected, because even though it's a free theory, correlation functions of these operators J are not trivial. So what we should compare between boundary and bulk are correlation functions of these single trace operators. For example, 3-point functions. Let's say a 3-point function of 3 of these currents, JS1, JS2, JS3. This is a very simple calculation. In the free theory, it's just a Feynman diagram where, so these operators are all bilinears. So let me just write this schematically like this. So if you want to compute this in the free theory, you'll just do free weak contractions of these operators with the free phi propagator. And this is just a simple Feynman diagram, right? So do you know what I mean by this Feynman diagram? So this is, each of these vertices is the bilinear current, and these are the propagators. So this is a free theory, but this is non-zero, of course. You can just explicitly calculate it. It's non-zero. It's some number times some tensor structure which depends on the spins. And if we think about how we usually compute this from AdS, then in the AdS point of view, we are computing a Witten diagram like this, where this is the boundary, these are the 3 currents. So in order to reproduce the non-zero answer for this correlator, we must have some non-trivial interaction in the bulk, which is, of course, what we expect from Vasiliev theory, which is an interacting theory. Okay, so here there is some interaction, G bulk. Okay. If we normalize the currents so that Jj scales as 1, which means that the Js is 1 over square root n phi. Let me drop indices in this schematic here. Okay, then the 3-point function, it's easy to see that it scales like 1 over square root n, because this loop gives a factor of n, and each of the operators with this normalization carries a 1 over square root n. So that means that in the bulk, this coupling constant goes like 1 over square root of n, which is the usual thing that we expect in AdS CFT. The large n limit on the CFT side corresponds to a weak coupling expansion on the AdS. So this says that in this vector model, AdS dualities, the coupling constant in the bulk goes like 1 over square root of n, and in terms of Newton constant, which is what usually appears in front of the bulk action, something like this. This means, so G bulk, so usually what we put here is 1 over coupling constant square. So that means that in this dualities, Gn goes like 1 over n at large n. This is just a large n, so to leading order approximation, we know that it goes like this. This doesn't preclude the possibility that there are order 1 shifts here, which is what Igor explained yesterday, which seems to happen in the case of ON vector models. as I will review later on. But to leading order large n, this means that G Newton goes like 1 over n, and this is different. So there is an n here in front of everything. This is different from the usual Yang-Mills type AdS CFT dualities, where the Newton constant scales like n squared. So this is a feature of this vector model dualities. The Newton constant scales like n. Okay. So here I wrote schematically an action which involves the Einstein term, and so here there are, of course, other terms which come from this theory. We don't really know the Lagrangian, but it will take a form here where the Einstein gravity is corrected by some interactions. So one question that you may ask is whether the gravitational part of this action, once you disregard all the higher spin fields, is the same as Einstein gravity or not. To answer that question, you can think about the 3-point function of stress tensor in these vector models. So if you want to calculate the 3-point function of the stress tensor, that corresponds to leading order to this diagram where this is the metric, the field dual to the stress tensor, and this is the cubic coupling of the graviton in this theory. Now, in this vector model, you can calculate TTT in this free scalar, and that answer does not agree with what you would get if you calculate this diagram with the pure Einstein action. This is a calculation that was done several years ago. So let me just remind you that in general, for any CFT in 3D, just by imposing conformal symmetry and conservation of the stress tensor, this is in general a linear combination of two pieces. One is the TTT corresponding to a free scalar, and the other is the TTT corresponding to the free fermion. Okay, so this is just true in any CFT. These coefficients are fixed by the model, but this is always, there is this decomposition. And if one uses just Einstein gravity in the bulk, what one gets is a sum of these two terms. This is a calculation that was done long ago by Arutyunov and Frolov. So that cannot agree with just this vector model where we only supposed to get the free scalar piece. Okay, so these coefficients can be changed if in the bulk we have modification to the Einstein gravity. So if, for example, here there are higher derivative corrections, R cubed and so on, then if you do this calculation in AdS CFT, you will find different coefficients. Okay, so this shows that even if we don't know the details of Vasiliev theory, if it's really dual to this simple scalar vector model, it must be a higher derivative modification of Einstein gravity in the gravitational sector. It must include these higher derivative terms, because without those, you will not be able to get the TTT of a free scalar. Okay, so so Vasiliev theory is in particular a higher derivative theory of gravity. And if one analyzes the equations of motion, you can explicitly see this. There are interactions which involve higher derivatives. The free part is the same as Einstein gravity, but interactions involve higher derivatives. Okay. Any questions? Okay. Okay, so from all these arguments, even if we didn't know Vasiliev theory, we would conclude that some consistent theory of interacting higher spins should exist in AdS because it must be dual to these simple free CFTs. And indeed, it's good that it exists, and it was constructed even before AdS CFT. And all the features of Vasiliev theory agree with all that we expect from these simple arguments. Okay, so let me also mention that even though I was describing here the UN theory, one can also consider the ON theory. So take instead take instead a theory of n real scalars with an ON invariance, then most of what I said can be repeated. The only difference is that there are only even spin currents. So if we consider ON theory with real scalars, then the spectrum here would be similar, but there are only even spin currents, because for real fields you cannot write down the odd spin currents. As you can see from the spin 1 case, if phi was real, that would be identically 0. And this, as a natural counterpart on the Vasiliev side, it corresponds to a consistent truncation of the Vasiliev theory to a theory which is so-called minimal Vasiliev theory, in which the spectrum is indeed scalar plus s equal 2, 4, 6, and so on. Okay, so you can consider UN or ON. In the bulk, the difference is that you can do a consistent truncation to even spins only, and the equations of motion are the same. Okay. Sorry? USPN group. SPN. Yeah, you can also consider USPN group. That it will be dual to a different type of Vasiliev theory, which, well, in that case you have more operators. You have yeah, I think you have a triplet of even spin operators and a single tower of odd spin operators. You can consider that case, USPN. So you can view that as a subgroup of the unitary group, and there is a corresponding Vasiliev theory with a slightly different spectrum. Okay. Yeah. Sorry, say that again. Have I ruled out?
Have you already ruled out the sitter?
No, I haven't. No, the sitter is a possibility, but I'm focusing on AdS CFT, so I'm not discussing the sitter story. But there is a Vasiliev theory with negative or positive cosmological constant. The one with positive cosmological constant as the sitter solution. So you have a consistent theory of interacting higher spin fields in the sitter space.
Yeah, but the question is whether you can propose a version of this correspondence for the sitter.
Well, there are versions not of AdS CFT, but of DS CFT correspondence. Yes, this is what Strominger and collaborators did. So the proposal is that they are also dual to some free vector models, but they are vector models in which scalars are anti-commuting. So some kind of ghost-like scalars, and so in Euclidean 3 dimensions. And that can be understood essentially as an analytic continuation from n to minus n, which corresponds to sending cosmological constant to be positive instead of negative. But I'm not going to discuss those, but there are proposals for the SCFT versions of this. Any other question? Yeah. Sorry? You want to know if I'm going to discuss that, or? Okay, so in 4-dimensional space, there are no mixed symmetry fields, or the higher spin fields are totally symmetric fields. If you go to higher dimensions, there are possibilities of having these mixed symmetry fields, and the fully nonlinear theory of Vasiliev type for those theories is not known. You can write down the spectrum, and for example, if you have a free fermion CFT in 4 dimensions, if you list all the operators, you see that there are some operators which are mixed symmetry type, and those should be dual to some mixed symmetry field in AdS5. but the fully nonlinear theories are not known for those. You can deduce the spectrum, and you can write down the free equations of motion. Any other question? Okay. So we've seen that it seems to be very natural to propose that these free vector models are dual to Vasiliev theories. And the first paper which clearly made this statement was the paper by Klebanov and Polyakov in 2002. But what was a crucial observation of that paper is that we're not restricted to just studying free theories. Of course, this is already interesting because it's a very simple example of AdS CFT in which we have in principle an exact duality between a very simple non-supersymmetric CFT and some gravitational theory with higher spin fields. So that's interesting from a conceptual point of view, but from physical point of view, maybe it would be more interesting to study interacting CFTs, not just free CFTs. And what Klebanov and Polyakov pointed out is that we can indeed also describe interacting CFTs in the same framework. So this was also reviewed yesterday. So again, well, let me now here do ON, but you can do UN case as well. So consider, instead of the free theory, an interacting theory in which you had the quartic interaction for these scalar fields. So this was also reviewed briefly yesterday. So if you are in dimension between 2 and 4, this interaction term is relevant. And you expect that the theory flows from a free theory in the UV to an interacting theory in the IR. That interacting theory is the famous Wilson-Fisher fixed point. It can be studied in the 1/n expansion directly in the equal 3 or in any dimension, or it can be studied perturbatively in the 4-epsilon expansion where you have a perturbative fixed point by studying the beta function for this theory. Okay, what Klebanov and Polyakov pointed out is that you can view this quartic interaction as a special case of a more general class of interacting CFTs which are obtained by deforming some CFT by a double trace operator. So this is, in this context, is what we would call a double trace operator because it's the square of a single trace operator. So this is the operator I was calling J0 before. So this is a special example of deforming a CFT by a double trace operator where there's always this J0 in this case. And when this is this deformation is relevant to the formation of the theory, it is known in general, it can be shown by 1/n expansion, that then the theory flows from CFT in the UV where J0 has dimension delta, in this case delta equal 1. So you flow from the UV CFT, which in this case is a free CFT, to an IR CFT. So here dimension delta, and here dimension d minus delta UV. So in this case, this is 1, and this is 2 plus 1/n corrections. So this is some general results applied to this special case. What you can show by 1/n expansion is that this theory flows from the free theory in the UV, where this operator has the engineering dimension delta equal 1, which is just the dimension of I, to an interacting theory where the operator has dimension 2. Okay? And what is the what does this correspond to in the AdS language? So again, this is a special case of a general story where these double trace flows correspond to changing boundary conditions for the bulk field which is dual to this operator J0. So this operator J0 is dual to that scalar field in Vasiliev theory, which has mass square minus 2. And that mass square is precisely in the range where if you study the solution of delta minus t equal m squared, if you study the solutions to this equation, both solutions are above the unitarity bound and both are allowed. Yes?
No, 5 moments.
Oh, okay. So yes. So in this case, you'll find two solutions, delta equal 1 and delta equal 2, which are both above the unitarity bounds for scalars in d equal 3, which is 1/2, which means that on the AdS side, in principle, you have two possible choices for the boundary conditions that you want to impose on your scalar field. And the statement is that depending on that choice, you're either describing the UV fixed point, which in this case is a free theory, or the IR fixed point, which is this interacting Wilson-Fisher fixed point. So the bulk field, you impose that for, so I'm assuming here the Poincaré coordinates of AdS, which were given yesterday in the talk by Steve. So the boundary sits at z equals 0, and when you study this theory in AdS, you have to impose some boundary condition for phi. Boundary condition is that this goes as some power of z, and this power is fixed by the mass. And what I'm saying there is that this power can be either 1 or 2. If you fix 1, you are describing the free CFT at the boundary, and if you fix 2, you are describing this Wilson-Fisher fixed point. Okay, so this is this crucial observation of Klebanov and Polyakov is that the same Vasiliev theory can describe either the free CFT or the Wilson-Fisher fixed point, depending on the choice of boundary condition for the scalar. Okay, so if you analyze the operator spectrum of this Wilson-Fisher fixed point, you find that there are still these higher spin operators, of course, these bilinears with S derivatives. But because now because this theory is now interacting, the dimension of this higher spin operator at the Wilson-Fisher fixed point is not S plus 1, which is what we had in the free theory, but it's S plus 1 plus 1 over n corrections. So S plus 1 would be the dimension of conserved current. It just follows from conformal algebra. So, but here, because this is interacting, there are 1 over n correction. But what is important is that this anomalous dimension is not modified. This dimension is not modified to leading order in n. So these higher spin currents are still approximately conserved in the large n limit. So equivalent statement to this is that these currents of spin S are not conserved, but they are conserved in the large n limit. So explicitly, if you study the conservation equation for this currents, you find that schematically it takes this form. So the divergence is not 0, but what appears here is a double trace operator, is a product of one of these currents and the scalar operator, and there is a 1 over square root of n. So this means that these currents are approximately conserved in the large n limit, and these two essentially are equivalent. This implies that the anomalous dimension is only of order 1 over n, which means that at the classical level in the bulk, the dual fields are still massless. So that's why it makes sense that this theory can still be dual to the Vasiliev theory. At the classical level, you still have massless higher spin fields, and they acquire mass due to 1 over n correction, which in the bulk is loop corrections. Okay. I think I have to stop here, and if you have more questions, yes?